All right, I think we'll go ahead and get started here. Good afternoon, everybody, and this is usually the point in time where everybody starts to fall asleep. So we'll try to have a little bit of fun with Unity and Mathematica to wake you up with that after lunch low. My name's George Danner. I run a company in Houston, Texas, that builds computer simulations for businesses. We're not in the gaming industry. We don't build games. But in effect, we do. We really sort of do, because we build these simulation models of real-life corporate examples that we'd like to have the same sort of quality and essence, if you will, of a good quality game. So we try to mimic some of the visualization elements that they have. So we've got two things here to look at. You've got Mathematica, which is this amazing technical computing environment. And then you've got Unity, which is a very popular game engine. It's used in about 60% of the mobile games and a very large percentage of both the desktop and console games. And it's an open source gaming engine. It's very well engineered, extremely well designed, well supported. What happens when you put these two amazing environments together? So we thought we'd have a little fun by doing that, and in the course of making that linkage happen, perhaps build some simulation models that we just haven't seen before. There is a bit of a sort of a grander purpose, I guess, to the work that I'm doing in visualization. I happen to be writing a book at the moment. The book will be released early next year. Available from finer bookstores, by the way. Shameless plug for the book. But part of that book is about problem solving. And part of problem solving, as Conrad mentioned in his education talk, is about the visualization of the problem itself. So that's a big theme in what we're going to sort of look at and talk about. So let's look at these two environments. So Mathematica, of course, has great visualization capability, I mean, without question. However, you do have this game engine, Unity, that was designed specifically for very, very realistic 3D visualizations. One of my colleagues, Alan Savoy, sort of made this quote: what if we could have Mathematica as the writer, using the movie metaphor, and Unity is sort of the director in the film studio? In other words, could you create logic in Mathematica about the movement of objects in a realistic scene, and then come over to Unity and watch that scene play out? So last year, Todd Gailey and Luke also, who was off sailing around the world now, gave a talk about Unity Link. They built Unity Link, and that was a direct integration between Unity and Mathematica. I thought that was really neat, and based on their talk, inspired by their talk, we did a few little experiments, and we thought, well, you know, there's something to this whole idea of blending Unity with Mathematica. And it kind of repeats this general theme that we've had. This is our sort of third talk in a row about integration, which I think is an important and powerful capability of Mathematica. Not that it's great in its own right, which it is, but the fact that you can put it together with other unusual tools and create something even more amazing. So 2 years ago, we talked about the integration of Mathematica with Google technologies. Last year, we talked about integration of Mathematica with Twitter, of all things, and this year it's Unity. So some of you may not really be that familiar with Unity. So here's just a kind of a quick trailer that I sort of grabbed at random. But you know, what you can see is that Unity gives you really kind of the studio, if you will, the ability to create these amazingly realistic scenes. Now, so notice you've got some structure there, and you had some clouds. The particle system inside of Unity, in other words, how it represents sort of smoke and fire and other sort of fluids, is again another really well engineered part of Unity, and we We actually used it in one of our applications, which I'll show you. So I don't want to do too much of that. That's just, okay, so we know about games. We know how wonderful games are in the technical aspects of them. I mean, the gaming industry spends hundreds of millions of dollars. I don't know what the figure is, but they spend a lot of money getting the shading just right, getting the colors just right, camera angles, lighting, all of that. So the nice thing for us is that we can take all of that work and build on it with something like Mathematica. So the question is, how can we and should we link Mathematica in with something like that? So let's take a look. And there are a couple of ways when you look at, all right, so I want to integrate Mathematica with Unity. How do I do it? There's really it comes down to two different choices. Now what Todd and Luke built last year in Unity Link was something that very much looks like what you see here. You have Mathematica, and then you have, much like J-Link and R-Link and MathLink and all of the other sort of connection technologies built into Mathematica to allow you to talk to Unity and have Unity talk back to you. So in other words, it's as if Mathematica was sort of the puppet master and Unity contained the scenery with all the puppets that Mathematica could drive. It could say, all right, move this monster from here to there, or make this particular sword or weapon appear. So you could have Mathematica direct the things that are going on in Unity. And at the same time, you can have information coming back from Unity. So where are certain enemies located in the scene? Where are certain things, objects there? So you can get feedback and you can drive it in real time. The disadvantage that we saw when we looked at this approach was the whole idea of deployment. You know, when we build models for companies that want to have these models, you know, ultimately they want it deployed in some way that they can use them. And deploying Mathematica together with Unity in a sort of a tight coupling like that was a challenge. It's something we want to work on, though. So what we decided on was really kind of the architecture option number 2, which is on the lower part of that page right there, which is, all right, well, let's do it asynchronously. Let's have Mathematica generate a script, if you will, a script of commands. And these commands are in some protocol that we sort of dreamed up ourselves. And then have that read into Unity and have Unity act it out accordingly. It's kind of like the metaphor of a player piano, where you have the player piano script, the little dots cut out on the page, and you flow it through the player piano and it just sort of plays it away. That's kind of the way that we did this here for Unity. It becomes attached actually to the Unity project. So we settled on that, and then we said, all right, what's it going to take to sort of put that together? The big kind of design aspect of that was sort of the structure of the script. So it's a list of commands for the actors. So the scene itself is pre-built. So we actually had a studio work with us to build up sort of scenes and everything. And we asked them also to build sort of characters and objects for us. And then once you have those in place, it's almost like you have the actors on the stage. Then you give the actors a series of time-based commands to make them move around on the stage in the way that you want them to move around. So we built some code, and incidentally, the code is you know, it's a lot of fairly big functions. I'm not going to obviously go into a lot of this code, but it took a lot of code essentially to generate the script that looks like that right there. So for example, here's at time 55, I'm asking an object called HeloBox3 to move to a destination called HeloTarget 4. That's another thing that we sort of wanted to do with this script, is give it minimal information. In other words, in Mathematica, you don't have to know anything really about the object and how it's supposed to move from A to B. You just tell it, go move from A to B, then Unity figures that out, or should figure that out. In that way, I think we're taking advantage of the power of each environment. Mathematica is very good at sort of generating these scripts numerically, and Unity is very good at sort of portraying out the visualization. So that's just kind of a code fragment that I'm showing you here at some time 55, whatever that means in the time pacing here. I'm asking an object to move to a particular location. I'm also updating some data in Unity. I'm saying there's this metric called compliance, and I want it to have this certain value at that same time period 55. So it's kind of a structured list of commands, and Unity is going to be processing all this. And notice kind of an interesting thing over here. I'm actually sending it a little piece of graphic, a little spark line, if you will, per trail. So we're also in the commands, we're actually having Unity display a graph. Now here was something that sort of, if you will, violated our minimalist approach, because it turns out that Unity is really terrible at drawing graphs. And you can buy code modules in the Unity store that do certain things, but all the graphing ones were awful. So Mathematica is great at drawing graphs. So the question is, could we have Mathematica draw the graph and just send the image over to Unity? So a lot of the work that we did was sort of figuring all of that out and ultimately building a JSON file that then Unity can read. I mean, JSON is a native format, JSON, native format for Mathematica. It's also happens to be a native format for Unity. So there was where we found some sort of common ground between the two. We constructed the list of commands first, and then reformatted that into a JSON file that then Unity could directly consume. And we had to write a lot of code to kind of glue those parts together, but ultimately it worked fine. Like I said up here, it's the embedded graphics that were probably the biggest challenge, because we had to figure out how to break those down basically into text and what's called dehydrating a graphics image and then rehydrating it. In other words, rebuilding the graphic on the other side in Unity. That was a tricky part to this whole thing. Okay, so all right, so what did we do with this? So let's talk a little bit about the animations that we built, and I'll show you the animations here in just a minute. The first one was offshore logistics. We were approached by a really large oil company that wanted to drill for oil in West Africa. And in order to do that, you have to have an army, almost literally an army of ships and helicopters, moving personnel and moving equipment and materials back and forth from the shore out on the ocean to these various drilling rigs. And the exact timing of when these boats arrive and when the helicopters arrive is a sort of an intricate and very complex dance that's very expensive, by the way. If you could figure out a way to optimize those routes and take, say, one boat out of the system or one helicopter out of the system, each one of these vessels, these workboats offshore, rent for $55,000 per day. So you just do the math on that, and it's a lot of money. So a lot of our work was trying to figure out exactly the cadence of these deliveries for the boat. So let's take a look at what that's like. So here is our Unity portrayal. I'll back up just a little bit. Let's see. I can't see on the right-hand side. Let's see. Let me make it smaller so we can see. Okay, we can see it a little bit better now. All right, so the scene, and that's actually the Angolan coastline over there, was built for us. And these drilling rigs were built for us as well, these objects. And now, again, what we're doing is, you see them flying around in the air? What we're doing is we're directing the boats to go to certain places. We're directing the helicopters to go to certain places. So this is all driven by Mathematica. In other words, the game is there, and it's just waiting for these Mathematica commands, like the structure that I just showed you, to come through to say, all right, move this helicopter here, move this boat there. and we're keeping track over here on the right-hand side. Remember the spark lines? So these are the spark lines that are being sent over from Mathematica to Unity to then display on the heads-up display. This is another wonderful aspect of game engines is you can overlay these heads-up displays and show all kinds of metrics about what's going on. So you can even sort of back off the screen a little bit and woohoo, go under the water and see above and scoot around. It's and you can see, my MacBook Pro here is it's a reasonably good machine, but you can see how nicely and quickly it renders. Unity renders very, very efficiently. There's no sort of hiccups or anything to the screen as I'm sort of moving around this scene. So that's one assignment that we had, was to simply build this. And it's interesting, when we started showing the people, the oil company based in London, by the way, kind of this portrayal of the scene, they said, oh, that's interesting for a simulation model, but could you hook that up to a real-time sort of display so that I could sit in my nice, comfortable office in London and not have to fly out to Angola with the heat and the bugs and the dust and everything? And that certainly could be done. This could be attached to a real-time display just as easily. So you're, in a sense, watching something that looks very much like a weather weather report from WeatherBug or something like that. You're watching what's actually happening instead of a simulated forecast of what's going on. All right, so that was one assignment. That was a lot of fun to put together, and we were kind of amazed at how quickly we could put together. We built the scene in about 3 or 4 days, or a studio built the scene in about 3 or 4 days, and then we put the interface together in another sort of week or so. So Unity made it easy for us to do this. So the integration wasn't as difficult as we thought it would be, and I think that's really good news. All right, the second application that we had was one of oil and gas drilling. Another oil company came to us, oil field services company came to us actually, and were asking us about this whole unconventional drilling. Now you've probably heard all the press about fracking, hydraulic fracturing underneath to drive the oil and gas particles in the way that you want to drive them. Kind of controversial actually, but in essence the energy industry is really a bit flummoxed about this whole idea of unconventional drilling. Conventional drilling is you stick a pipe in a hole and out comes the oil. Unconventional drilling is much more like mining. It's kind of like mining underground. You're crushing rock underground. The technologies are different. The geology is different. It's different in every kind of way. So they wanted to really understand basically how does this viscous fluid, oil and gas and mud and water all mixed together, sort of moving through cracks in rock. So that's when we had a chance to work with what I think is a really powerful part of Unity, which is the particle system. And I think probably lots of applications of the particle system. Essentially, it allows you to take some medium that is particulate in nature, so fire or smoke or some kind of liquid or fog or clouds, and represent it in a real physics kind of way inside of Unity. It's a very kind of sophisticated and complicated system to work with, but it allows you a whole lot of flexibility. So the challenge for us was figuring out if in fact we could do this. So we created for ourselves a stimulation source. That's that blue pipe. So imagine that's the thing that's injecting this fluid in there, breaking up rocks. And then we created for ourselves an extraction source. So this is pipe that's going to suck up the stuff that comes its way. So when we do that, we can see that there's the gas and oil mixture. I believe the gas is the purple and the oil mixture is green. And still early days in this, we're still playing around with this, but essentially that's the way the stuff is moving through these rocks. We've cut the rocks away and made them invisible, and we're imagining this fluid sort of winding its way through these capillaries, ultimately headed toward the extraction source so it could be sucked up. And they're testing all kinds of technologies for making this work. And what they wanted to use was the combination of Mathematica to do the calculations, and then Unity to show how it actually worked. So in other words, Mathematica is doing the capillary flow calculations. We used this thing called lattice-Boltzmann equations to say, all right, this piece of fluid is going to move this way, and this piece of fluid is going to move that way, and wrote up all those calculations, generated another one of these script files, like I was showing you earlier, and it, in turn, makes the fluid flow. Because the particle system in Unity is so flexible, it allowed us to kind of program it, if you will, to make it move in the way we needed it to move, and color it the way we wanted to color it, and make it as dense as we needed to make it in order for it to be an appropriate kind of representation of a gas and oil mixture. So that's Mathematica driving that scene. I think if you had any one tool alone, it'd be really difficult to do something like this. But the fact that you've got the power of both is I think really, really helpful. Right. So the project that we have planned is then to kind of move into this more real-time environment. I mentioned real-time in that first example. So I think real-time is a real exciting place to go. Well, it turns out that the British government makes the position of every single train in the London Underground public every 15 seconds. So you just go to a web service, and you subscribe to that web service, and you can pull down the locations of every single train as it updates. So we thought, wouldn't it be cool if we could build this sort of replica of the entire London Underground system, and you could sort of swing around it like we were swinging around that other scene, and kind of watch the trains as they sort of move from one station to the other. So we're about 50% of the way there. Unfortunately, I didn't have anything to show you here, but that's where we're headed, so that we could sort of just prove that this real-time aspect can be integrated with Mathematica and Unity all together to give just a hyper-realistic view of what's going on. Okay, so let me just close with a couple of points. One is, what did we learn when we started doing all of this? I think there's really no question that Mathematica was perfect for doing this kind of work. So those two applications that I showed you, the kind of marine aviation logistics and the unconventional drilling, those are very different applications. Yet we found it very easy to do the logic inside of Mathematica, even though those were widely disparate kinds of applications. So we're very big on Mathematica being the kind of the right platform to do that kind of work. As I mentioned before, Unity has some drawbacks in that it's terrible at drawing graphs. So we decided to do that in Mathematica and serve that over to Unity. We're still looking at that, but I think for the foreseeable future, we'll probably have Mathematica doing things like time series graphs. One of my colleagues went to the Unity User Conference this year in Seattle, which was actually just a couple of months ago. And we're learning about future versions of Unity. There's a very active community working on Unity and upgrading, and I think the new version is version 5 that's going to be coming out. It's got some really good user interface aspects to it. And our overall conclusion is that Unity is going to be an even easier environment to link Mathematica up to, not harder. And once you do that linkage, you're going to have lots more applications that we could do. And sort of in that spirit, let's talk about some possible applications. I mean, your mind can go a lot of different directions when you think about how powerful this combination of the two platforms could be. I mean, one of the things that I believe could happen is a lot of medical imaging and medical reconstruction. I mean, you could fly through a body, in and out. You could zoom into a part of the body, or take the body and make it all glass and look at only certain organs or certain disease portions of the body. A lot of that is going on right now, but what I've observed, and I don't know a whole lot about medical applications, I do know a little, is they use very highly specialized software to do this. And I think the message here is that we can use open source software now to do really sophisticated medical visualizations. The other is, and I've come into contact every now and again with sports teams that we work with, and they're very interested in going kind of beyond Moneyball. How many of you know the Moneyball story or have seen the movie or read the book? Well, if you haven't, your homework tonight is to go home and rent that movie or read the book, because it's a great book about using essentially data science on sports, and that's all terrific. You know, looking at statistics, looking at the right metrics, but going beyond that and actually replaying certain game situations in a realistic kind of scene is going yet beyond Moneyball, which is a really exciting area. Manufacturing and logistics is another sort of classic application of this. If you could watch a supply chain or rip the roof off of a factory and look inside it and watch a day in the life of it, it gives you a really powerful way to kind of look at how to improve it. Large-scale infrastructure projects, we're working with the Qatari government on the Soccer World Cup in 2022. They've got lots of big infrastructure ideas about where to put hotels and soccer stadiums and the like, and working all of that out. We could do that with a lot of that with Unity, and certainly in teaching almost anything, Unity is a great platform. So I'll just kind of move really quickly on some of these. There's those heads-up displays are going to get a lot more elaborate. We're going to try to crack the code around this direct architecture idea using Unity Link, and not only controlling the actors on the stage, but what we'd also like to do is be able to control the camera, picture-in-picture, and swapping the two. Doing things with lighting, like putting spotlights on a particular actor and watching that actor through the scene. And then finally, if you don't know about Oculus Rift, I would suggest you Google it, because that's a sea change in virtual reality. Virtual reality headsets were in the thousands of dollars up until very recently. The latest development kit that they've released, $350. So what that's going to do is going to bring virtual reality to the mainstream. And by the way, Unity supports virtual reality, so any of these games can be done in a sort of a stereoscopic sort of way. And that's Oculus Rift right there, and that's the stereoscopic scene that you see. So I think there's lots of really exciting possibilities when we put Mathematica together with other really powerful things. So we're going to just keep going and see where it leads. With that, I'll conclude. Thank you very much.